Hello, my name is Raushana Timratova. I am a research assistant at Institute of Smart Systems and Artificial Intelligence. Today, I'm going to talk about machine learning basics, logistic regression. Before we start talking about logistic regression, let's recap linear regression. There are two types of linear regression: simple, one variable, and multiple variables. The equation for the simple linear regression is defined as f of x is equal to b0 plus b1x. The most common method to fit a regression line is the linear least squares regression, which minimizes the total squared error, which is shown on the slide. The minimum error occurs for the first parameter when the summation of 2b0 minus 2y plus 2b1x is equal to 0. The minimum error for the second parameter occurs when the summation of 2b1 x squared minus 2xy plus 2b0 x is equal to 0. If we solve the two equations dE by dB1 and dE by dB0 for the parameters b0 and b1, we get equations shown at the bottom of the slide. To see how formulas of simple linear regression work, let's look at an example where we need to find the relation of the weight to the height. Data points are given in the table and shown in Figure 1. By using the simple linear regression, we find the line as f of x is equal to 0.58x minus 33. By using this line, we can predict the weight of a person with a height of 165 centimeters as 62.7 kilograms. The extension of simple linear regression is multiple regression. It examines how multiple independent variables are related to one dependent variable. We choose a function to fit a dependent variable using k independent variables and m parameters. The total squared error minimization is mathematically denoted as shown on the slide, where I goes from 1 to n data points. By setting the gradient of the parameters to 0, the minimum total square error can be computed as shown at the bottom of the slide. Let's find the relation of the weight to height and age using multiple linear regression. We have two independent variables here, height x1 and age x2. Given data points are shown in Figure 2. Using multiple linear regression, we find the dependent variable as a hyperplane. So f of x1 and x2 is equal to 0.64x1 plus 0.28x2 minus 51.09. The hyperplane is shown in Figure 2. Suppose we want to predict an adult or a kid, which is 1 or 0 respectively, based on the height. Data points for this example are given in the table and shown in Figure 3. If we try to solve it using linear regression as shown in Figure 3, we get continuous variables. For example, when the height is equal to 75 centimeters, the predicted value is negative. Since the output must be 0 or 1, we cannot directly use a linear model to estimate f of x. To solve the classification problem, we can transform linear regression using a logistic regression curve. The process of converting from linear regression to logistic regression is following. Independent variables x are converted to probabilities of the event occurring using linear model. After that, probabilities are converted to values between 0 and 1 using sigmoid function. To understand logistic regression, first, we need to revise the concepts probability and odds. The probability that an event will occur is the fraction of times you expect to see that event in many trials. If the probability of an event occurring is p, then the probability of the event not occurring is 1 minus p. Probabilities always range between 0 and 1. The probability of the output being 0 with given samples x is represented on the slide. Odds of the event can take any value from 0 to infinity. Values greater than 1 associated with an event being more likely to occur than not to occur, and values less than 1 associated with an event that is less likely to occur than not occur. Odds are represented as p divided by 1 minus p. Let's assume the probability that it will rain is 60%. Hence, the odds of the event are p divided by 1 minus p, which is 0.6 divided by 1 minus 0.6. Hence, odds is equal to 1.5. Now, let's transform probability to logistic regression. Logarithm of odds is equal to b0 plus b1x. By manipulating this equation, we get that probability, which is f of x, is equal to 1 divided by 1 plus e to minus b0 plus b1x. Overall, logistic regression is a supervised learning method for predicting binary variables. It categorizes data into discrete classes by studying the relationship from a given set of labeled data. It learns a linear relationship from the given dataset and then introduces a nonlinearity using the sigmoid function, which is shown in Figure 4. The sigmoid function returns a value in the range of 0 to 1 and is used to get binary output 0 or 1. If the function value is between 0 and 0.5, then the binary output is 0. If the function value is between 0.5 and 1, then the binary output is 1. For our example, where we want to predict an adult or a kid based on the height, the sigmoid function is shown in Figure 4. The function is equal to 1 divided by 1 plus e to minus 176 plus 1.3x. When the height is equal to 75 centimeters, a predicted value is close to 0. Hence, the class is a kid. To estimate b0 and b1 coefficients, we minimize the error or log loss function which measures the accuracy of a classifier. The log loss function is shown on the slide. Using logistic regression, let's find if a student passes the exam knowing the time spent on learning, which is shown in the table in the columns of xi and yi. To solve the problem, let's assume that b0 is equal to -4 and b1 is equal to 0.5 and fill the following table. Knowing the coefficients, we can fill the column b0 plus b1 xi. With given coefficients b0 and b1, probability of each case is calculated. Log loss of each data point is estimated and shown in the table. Knowing the loss at each data point, we calculate the total log loss, which is equal to 1.35. Next, we change the values of b0 and b1, update the table, and recalculate the total log loss. We repeat the procedure while the loss is not minimized. Minimization of log loss is carried out iteratively by any iterative minimization scheme, such as the steepest descent or Newton's method. For this example, we used Newton's method. Hence, we get that b0 is equal to -3.33 and b1 is equal to 1.42, and the overall function is as shown on the slide. Now, using the sigmoid function, which is shown in Figure 5, we can predict if a student passes the exam based on the time spent on training. If the output is between 0 and 0.5, then a student will fail the exam. If the output is between 0.5 and 1, the student will pass the exam.